Welcome to the deep dive. Today we're plunging into, well, a really vast and vital subject, Earth materials and resource management.
It really is huge.
Think of this as your uh, express route to understanding everything from the rocks beneath our feet to the atmosphere way up above, and how our lives are just so deeply connected to it all.
Exactly. We've synthesized a whole load of information, really, touching on the fundamental building blocks of our planet, rocks and minerals,
Right.
and then exploring the energy that powers our civilization, the food we grow, the water we rely on, those huge oceans, and even the natural forces, the hazards that shape our landscapes.
And we'll also look at the atmosphere, our growing global population, and the intricate web of natural ecosystems.
That's the plan.
Our goal today really is to reveal the crucial links between these things that might seem separate. We want to give you a clear, kind of digestible grasp of how Earth's systems and resources are intertwined.
And critically, the widespread effects of our actions on them.
Yes. Why should this matter to you, the listener? Well, because understanding these connections is just essential for tackling the challenges we face, from local environmental stuff to, big global issues like climate change and resource availability.
Couldn't agree more.
Okay, let's begin. Let's dig into the ground itself, rocks and minerals.
Right, let's start with the basics. We generally talk about three main kinds of rocks: igneous, sedimentary, and metamorphic.
Okay.
Igneous rocks, they come from molten rock cooling down and solidifying, either magma under the surface or lava that's erupted.
Oh, yeah.
If it cools quickly, like basalt at the surface, you get small crystals. But slow cooling underground, like with granite, lets larger crystals form.
Makes sense.
Then you have sedimentary rocks, things like limestone, sandstone, shale. They're formed when existing rocks break down, and the fragments get moved around, deposited in layers, and then sort of squashed and cemented together over time.
Like layers of history, almost.
In a way, yes. And finally, metamorphic rocks, marble and slate, are good examples. They happen when existing rocks get changed, transformed by intense heat and pressure, but without actually melting.
So they morph, basically.
Exactly. And all these processes, they're part of the rock cycle, this continuous transformation. Understanding these basic differences is, well, it's crucial if you want to find specific mineral resources. It shows that practical connection right away.
That makes sense. So when we talk about getting the valuable stuff out the minerals, how do we even start looking for them?
The search. It begins with exploration. Prospecting is the old school way, literally searching the ground.
Boots on the ground.
Right. But now we also use remote sensing a lot. Aerial photos, satellite images, lets us cover huge areas efficiently in almost any weather.
Technology helps there.
Definitely. Then there's geochemical analysis, taking rock samples, analyzing their chemistry, and geophysics, using physical properties, like sending seismic waves down and seeing how they reflect back to map out what's below.
Okay, so we've used these techniques, found a promising spot. What's next? How do we actually get the minerals out?
Well, that really depends on how deep the deposit is and where it is. For stuff near the surface, we use surface mining. That includes open pit and strip mining.
Open pit sounds like a big hole.
It is. You clear the land, maybe use explosives to break up the rock and then haul it away. Strip mining is more for thin layers, like coal seams. You remove the soil and rock on top the overburden in strips to get at the mineral layer.
And if it's deeper?
Then you need subsurface mining. Deep shaft mining is the classic example. You dig a vertical shaft down, then horizontal tunnels out to reach the ore and bring it back up to the surface.
Oh, sounds like a massive undertaking either way. What are the key things people weigh up when deciding if a deposit is even worth mining?
Oh, several critical factors. Cost is obviously huge: exploration, extraction, processing. Open pit tends to be cheaper per ton than subsurface. The geology itself is vital. You want high-grade ore, meaning more valuable metal per ton of rock. That makes even smaller deposits more attractive economically.
Right, the concentration matters.
Hugely. Then there's accessibility. Can you actually get equipment in and the ore out easily? Transport costs add up.
Sure.
And environmental impact assessment is mandatory now in most places. Companies have to show how they'll manage the damage and restore the site before they get permits.
That's important.
And finally, market forces. Simple supply and demand. If demand for a mineral shoots up, prices rise, and mines that weren't profitable before might suddenly become viable.
It's a really complex calculation then.
Yeah.
And speaking of consequences, what are the actual effects, good and bad, of all this digging?
They are substantial and, yeah, definitely varied. Environmentally, the big one is habitat destruction clearing vegetation. There's noise pollution from machines and blasting.
I can imagine.
Water contamination is a major issue. Water running through mine waste can become acidic and dissolve toxic metals.
And that gets into the ecosystem.
Exactly. It can build up in organisms, that's bioaccumulation, and then get more concentrated as it moves up the food chain. Biomagnification. That can seriously harm top predators.
Nasty stuff.
Plus, land pollution from waste dumps can stop plants growing. Air pollution from dust affects breathing and photosynthesis. And visually, mines can be quite impactful on the landscape.
But there are economic upsides too.
Yes, absolutely. Mining creates jobs, brings in tax revenue for governments, boosts export earnings, and often leads to better local infrastructure, roads, power, things like that.
And social impacts.
Can be positive too sometimes. Better access to services like healthcare and education might come along with the development. But there can also be social disruption, of course.
So once the mining stops, what happens to the site? Can you really fix the land afterwards?
Landscape restoration is, or should be, a key part of the plan. First, you need safe disposal of the waste rock and tailings to prevent collapses or ongoing pollution. That needs careful monitoring. Then the land restoration itself. It might involve refilling pits, bringing back topsoil, adding fertilizers, and replanting with native species.
Did that work?
It can, over time. There's also bioremediation, using living things like specific microbes or plants that accumulate metals to clean up pollution. You can do it on-site, in situ, or remove the contaminated soil for treatment, ex situ.
Interesting. Using nature to fix it.
Sometimes, yes. And eventually, restored mine sites can even become nature reserves, lakes, useful spaces again. It contributes to biodiversity recovery.
That's good to know there are efforts. Now, thinking bigger picture, how does this all relate to using resources responsibly? What do terms like sustainable resource and sustainable development actually mean here?
Good question. A sustainable resource is basically one you can use without running out because it replenishes itself fast enough, think timber from a well-managed forest. Sustainable development is broader. It's about meeting our needs today without messing things up so badly that future generations can't meet their own needs. For rocks and minerals, it means finding ways to extract and use them that minimize depletion and environmental harm in the long run.
So how do we actually do that? What are the strategies for using these finite resources more sustainably?
It really boils down to efficiency, both in getting them out and using them. We can improve extraction efficiency by maybe reprocessing old mine waste, using new chemical or biological techniques to get more metal from the ore, or just using better machinery.
Getting more from less rock.
Exactly. And on the consumption side, we need to use less material and products in the first place, and crucially, recycle. Recycling metals usually takes way less energy than making them from raw ore.
Recycling is key then.
Absolutely. And legislation helps drive this. Things like regulations for recycling electronic waste, WEE, for example, force us to handle things better.
Right. Okay, so that covers rocks and minerals. Let's shift gears now to another fundamental resource that, well, basically runs our modern world. Energy.
Yes, energy. It's fundamental, and understanding where it comes from and its impacts is, well, essential. Fossil fuels, coal, oil, natural gas, they were formed millions and millions of years ago.
From ancient life, right?
Exactly. Coal, mostly from giant prehistoric forests that got buried and compressed. Oil and gas, mainly from tiny marine organisms buried on the seabed, cooked by heat and pressure over ages.
And we classify energy sources based on how quickly they form.
Pretty much. We talk about non-renewable resources, the ones we're using up much faster than they can form. That's fossil fuels, and also nuclear fuels like uranium.
Finite supplies.
Right. And then there are renewable resources, the ones that replenish naturally on a human timescale. Things like geothermal heat from the earth, hydropower from rivers, tidal energy, wind, solar power, and biofuels grown from plants.
So quite a range. How do these different sources actually generate the electricity we use constantly?
The methods vary quite a bit. For fossil fuels and nuclear power, the common approach is to use the heat source to boil water, create high-pressure steam.
Which turns a turbine.
Precisely. The steam spins a turbine, which is connected to a generator, and that converts the rotational energy into electricity.
Okay, the steam turbine's pretty common then. What about the others?
Geothermal taps into heat from underground, using naturally occurring hot water or steam to drive turbines. Wind turbines, obviously, use the wind's energy to turn blades connected to a generator.
More direct.
Yes. Solar photovoltaic cells, or PV cells, convert sunlight directly into electricity, no moving parts needed there. Tidal barrages work a bit like hydro dams, using the flow of tides, while wave turbines capture the energy in ocean waves.
And hydroelectric.
That uses the force of water falling from a dammed reservoir to spin turbines and generate power.
That's a really diverse set of technologies, but I assume each one has its own pros and cons.
Oh, absolutely. Every single one. Fossil fuels, well, the technology is mature, infrastructure exists, they provide jobs, and they're relatively abundant in some places, but they're non-renewable. Burning them releases huge amounts of CO2. The main greenhouse gas in its extraction itself can be very damaging environmentally. Think oil spills or habitat destruction from mining.
Okay. What about nuclear?
Nuclear power can generate a massive amount of energy from a tiny amount of fuel with very low CO2 emissions during operation, and the fuel supply is large.
Sounds good, but the risks.
Exactly. The risk of accidents, though low, can have catastrophic consequences.
Yeah.
Managing the radioactive waste safely for thousands of years is a huge challenge, and the upfront cost of building plants is extremely high.
Right. And renewables, the clean options.
Renewables like wind and solar are sustainable and don't produce CO2 while operating, which is fantastic, but their output often depends on the weather or the location. Sunshine, wind
Don't forget.
speed, that's the word. They can also have visual impacts on the landscape, and some, like geothermal or big hydro projects, can have high initial costs or specific environmental impacts like flooding land for reservoirs.
Even biofuels aren't perfect.
They're renewable, and the plants absorb CO2 as they grow, which is good. But burning them still releases emissions, and growing biofuel crops can take up huge amounts of land, potentially competing with food production.
Lots to weigh up. Thinking about how much energy we all use, what drives that demand? Is it just population growth?
Population is part of it, but it's more complex. Domestically, higher incomes usually mean more energy, use more appliances, bigger houses, more travel. Economic conditions matter too. Demand often dips during recessions.
Makes sense. And industry.
Industry is a huge consumer, especially manufacturing. Advances in technology can sometimes increase efficiency, but overall industrial activity drives demand. And global trade means more energy needed for transport shipping, aviation, trucking.
And
Climate plays a big role too. Colder places obviously need more energy for heating and lighting in winter. Hotter places increasingly use a lot for air conditioning.
So with demand generally rising, how can we manage our energy use more effectively?
Efficient energy management is key, and it involves a whole range of things. Reducing consumption is the first step. Simple things like turning off appliances, using energy-efficient models, choosing walking or cycling instead of driving.
Individual actions.
Yes, but also broader strategies. Reducing energy waste is crucial. Better insulation in homes and buildings makes a huge difference. Programs like scrappage schemes can encourage people to replace old, inefficient cars or appliances.
What about getting energy from waste?
That's another angle. Anaerobic digestion of organic waste produces biogas, which can be burned for energy. Burning non-recyclable waste directly can generate heat and electricity, even reusing things like waste cooking oil as biofuel.
Interesting. And policy.
Policy is vital. Education campaigns can raise awareness. Legislation can set stricter energy efficiency standards for buildings and products, even banning the most inefficient ones.
And transport seems like a big target.
It is. Transport policies can include things like emissions tests for vehicles, restrictions or charges for driving high-emission vehicles in cities, carbon taxes on fuel, investing heavily in public transport and cycling infrastructure, promoting car sharing, and offering incentives for buying electric or fuel-efficient vehicles. It's a whole package.
It sounds like a really comprehensive approach is needed. What about finding new sources? Fracking gets talked about a lot. What's the deal with that?
Right, fracking or hydraulic fracturing. It's a technique to get oil and natural gas out of shale rock where it's trapped in tiny pores. They inject a high-pressure mix of water, sand, and chemicals deep underground to crack the rock open.
And the pros and cons.
Well, the potential upsides are accessing huge reserves of oil and gas that were previously unreachable. Natural gas burns cleaner than coal, so it can potentially reduce air pollution in some contexts compared to coal power. And it creates local jobs.
Okay, but the downsides.
There are significant concerns. The potential for the fracking fluids or methane itself to leak and contaminate groundwater is a big one. It uses very large amounts of water, which is a problem in dry areas. There's evidence it can trigger minor earthquakes, and the drilling operations cause noise and disruption.
Definitely controversial. Turning to the oceans for a moment, oil pollution is a major environmental disaster. What causes these spills and what happens to marine life?
Yeah, marine oil pollution is devastating. It can happen during offshore drilling operations, from leaks or ruptures in underwater pipelines, or perhaps most famously from accidents involving oil tankers.
And the impact.
It's severe, across the board. Phytoplankton, the base of the food web, can be killed off by oil slicks, blocking sunlight. Fish suffer, their gills get clogged, they ingest toxins, their food sources disappear. Awful for birds and mammals, too.
Terribly. Seabirds and marine mammals get coated in oil. It destroys the insulating properties of their feathers or fur, making it hard to stay warm. They ingest it when trying to clean themselves. It makes it difficult to move, fly, or swim, often fatal.
And coral reefs. Beaches.
Coral reefs can be smothered and die. Beaches get contaminated, killing intertidal organisms and hitting tourism and local economies hard. It's just a mess.
A really grim picture. What can be done to prevent spills and to clean up when they inevitably happen?
Prevention is key. Strong international rules, like the MARPOL Convention, set standards for tanker design and operation to minimize pollution risks. Double hulls on tankers, for example.
And cleanup.
When a spill occurs, the response involves trying to contain it with floating barriers called booms, using chemical dispersants to break the oil into smaller droplets, though that has its own potential impacts. Skimmers are boats that physically remove oil from the surface. And then there's often just painstaking manual cleanup on beaches. A huge effort. Okay, let's pivot again. Another fundamental need: food. Let's talk about agriculture and its environmental connections.
Right, agriculture, absolutely fundamental. And it all starts with the soil. Soil isn't just dirt, it's a complex mix. Mineral particles from broken down rock, organic matter from dead plants and animals, air in the spaces, and water.
And the particle size matters. Sand, silt, clay.
Hugely. Sand particles are the largest, silt is medium, clay is tiny. This mix determines the soil's texture, how well it drains, how much air it holds, and how well it holds onto nutrients. Sandy soils drain fast. Clay soils hold water tightly.
So soil is more than just something plants sit in. What does it actually do for them?
Oh, it provides everything plants need to grow, basically. Water, obviously. Essential mineral nutrients, nitrogen, phosphorus, potassium, and others. Oxygen for the roots to respire. And it anchors the plant, holds it upright.
And the organic stuff. Humus.
The organic matter is vital. Decomposers like worms, fungi, bacteria break it down into humus. Humus is incredibly rich in nutrients, and it also improves the soil structure, makes it more crumbly, better aerated, better at holding water. Soil pH, its acidity or alkalinity, is also critical because it affects which nutrients are actually available for the plants to take up.
We often hear farmers talk about sandy versus clay soils. What are the main differences for growing things?
Well, sandy soils, because of the large spaces between particles, drain really well, sometimes too well, washing nutrients away, but they warm up quickly and are generally easier to plow or cultivate.
And clay.
Clay soils have tiny particles, so they hold water and nutrients much better. That's good in some ways, but they can get waterlogged easily, they're slower to warm up, and they can be really heavy and difficult to work, especially when wet or very dry. Farmers definitely need different approaches for each.
There seem to be so many ways people farm around the world. Can you give us a quick rundown of the main types?
Sure. We can classify farming in a few ways. There's subsistence farming, basically growing enough just to feed your own family, maybe with a tiny bit left over.
Versus commercial?
Right. Commercial agriculture is all about growing crops or raising animals to sell in the market. Then you can distinguish between arable farming, which is growing crops.
Like wheat or corn.
Exactly. And pastoral farming, which is raising livestock, cattle, sheep, etc. Mixed farming does both.
Okay. And intensive versus extensive?
Extensive farming uses large areas of land, but with relatively low inputs, like maybe large cattle ranches. Intensive agriculture aims to get the maximum possible yield from a smaller area, using lots of inputs like fertilizer, pesticides, and often mechanization.
Getting those high yields is often the goal, especially with intensive farming. What techniques do farmers use to boost production?
A whole toolbox of techniques. Crop rotation is a big one, planting different crops in sequence on the same field. It helps break pest and disease cycles and can improve soil fertility, especially if you include legumes like beans or clover that fix nitrogen.
Smart. Fertilizers too, I assume.
Definitely. Both organic fertilizers like manure or compost and inorganic or chemical fertilizers that provide specific nutrients directly. Irrigation is key in many areas to provide water when rainfall isn't enough, using sprinklers, drip systems, and so on.
Controlling pests.
Yes, through various methods. Biological control uses natural predators of pests. Pesticides, chemical insecticides, and herbicides are widely used but have downsides. Mechanization tractors, combine harvesters allows farmers to work much larger areas efficiently, but clearing land for big machines can mean habitat loss.
And manipulating the plants themselves.
Absolutely. Selective breeding has been done for centuries to improve crop traits. More recently, genetic modification, GM, allows scientists to insert specific genes for traits like pest resistance or higher yields. And controlled environments, greenhouses, polytunnels, even hydroponics, where plants grow without soil, allow precise control over conditions.
Hydroponics sounds interesting. Pros and cons.
Yeah, hydroponics can give very high yields, uses less water overall, and avoids soil-borne diseases. But the setup costs can be high, it needs careful management and technical know-how, and it relies on nutrient solutions.
These intensive methods sound like they could have some negative side effects,
Yeah.
environmentally speaking.
They certainly can. Many conventional practices come with significant environmental and sometimes human health impacts. Overusing herbicides and insecticides, for instance, can lead to pests developing resistance, and it can harm beneficial insects, like pollinators.
Right, like bees.
Exactly. Overusing fertilizers is another big one. Excess nutrients wash off fields into rivers and lakes that's leaching and cause eutrophication.
Eutrophication.
That's when the excess nutrients cause massive blooms of algae. When the algae die and decompose, it uses up all the oxygen in the water, killing fish and other aquatic life. High nitrate levels in drinking water from fertilizer runoff can also cause health problems, like blue baby syndrome in infants.
Wow, what about irrigation issues?
Poorly managed irrigation can cause problems too. In dry areas, it can lead to salinization, a buildup of salts in the soil that harms plants. Waterlogging can occur if drainage is poor. It can also wash away nutrients or cause surface runoff carrying pollutants.
And just
Overproduction driven by subsidies or market demands can lead to huge amounts of food waste. Plus, continuously growing the same crop without putting nutrients back can exhaust the soil, making it less fertile and more prone to problems. Soil erosion is a massive issue. And sometimes the push for cash crops for export can mean less land is used to grow basic food crops for local people.
soil erosion sounds particularly bad. What actually causes it?
Several things often work together. Removing vegetation, whether forests or natural grassland, leaves the soil bare and exposed. Overcultivation, plowing too often or at the wrong times, breaks down the soil structure. Overgrazing by livestock removes plant cover and compacts the soil with their hooves.
And then wind and water take over.
Precisely. Strong winds can just blow dry topsoil away. Heavy rain can splash soil particles loose, and if the water can't soak in quickly, especially on compacted soil or slopes, it runs off the surface, carrying soil with it, sometimes carving out deep gullies.
And the consequences of losing all that topsoil.
They're severe. You lose the most fertile layer of soil, the part plants need most. That reduces crop yields. It's also habitat loss for countless soil organisms. The eroded soil ends up in rivers and lakes, silting them up, which harms aquatic life and can even make flooding worse downstream. In extreme cases, it leads to desertification, fertile land turning into desert.
A really serious problem. So what can farmers actually do to stop their soil washing or blowing away?
Thankfully, there are many effective strategies. On slopes, terracing, creating flat steps, or contour plowing, farming across the slope instead of up and down, dramatically slows water runoff.
Simple but effective.
Yes. Building bunds, which are small earth banks along contours, also helps hold back water in soil. Planting windbreaks rows of trees or hedges shelters fields from the wind.
Protecting the surface itself.
Crucial. Keeping the soil covered as much as possible is key. That could mean planting cover crops during fallow periods, leaving crop residues on the surface instead of plowing them in sometimes called no-till or minimum tillage farming. Adding organic matter like compost improves soil structure, making it less erodible and better at absorbing water.
Other techniques.
Planting trees, especially on erosion-prone areas, helps stabilize the soil. Mixed cropping or intercropping, growing different crops together in the same field, can provide better ground cover than a single crop. And crop rotation, as we mentioned, helps maintain soil health generally.
So putting it all together, what does sustainable agriculture actually look like? What's the goal?
The main aim of sustainable agriculture is to produce enough food for people now and in the future, but doing it in a way that minimizes harm to the environment, uses resources like water and energy efficiently, works with natural ecological processes instead of against them, and is also economically viable for the farmers themselves.
And the specific methods.
It often involves using organic fertilizers instead of relying solely on chemicals, managing livestock grazing carefully to prevent overgrazing, using crop rotation extensively, potentially using crop varieties that are naturally resistant to pests or drought, employing water-saving irrigation like trickle-drip systems, and harvesting rainwater where possible. It's about working smarter with nature.
Makes a lot of sense.
Hmm.
Okay, let's move on to another resource that's absolutely essential for all life. Water.
Water, yes. Covers most of the planet, but it's surprising how little is actually fresh water we can easily use. About 97% is salty ocean water.
Wow, only 3% fresh water.
Roughly, yes. And most of that fresh water is locked up in ice caps and glaciers. Then a big chunk is groundwater, hidden underground. Only a tiny fraction is in lakes, rivers, and the atmosphere. Understanding the water cycle evaporation, condensation, precipitation, runoff is fundamental to managing it.
But where do we actually get the fresh water we use every day?
Our main sources are aquifers, these underground layers of rock or sediment that hold groundwater. Sometimes, if the aquifer is under pressure, an artesian aquifer, water might rise to the surface on its own.
Or we drill wells.
Exactly. Wells tap into groundwater. We also get a lot of water from surface sources, rivers, lakes, and reservoirs, which are often artificial lakes created by building dams.
Reservoirs. They holding tanks?
Big ones, yes. There are also smaller surface reservoirs that store treated drinking water before it goes into the pipe system. And in very dry places, desalination plants are increasingly important, taking the salt out of seawater to make it drinkable.
How did they do that?
Two main methods. Distillation, which basically involves boiling the water and condensing the steam, leaving the salt behind, and reverse osmosis, which uses high pressure to force water through membranes that filter out the salt. The goal is to produce potable water safe to drink.
We use water for so much. Can you break down the main uses?
Sure. Domestically, it's drinking, cooking, washing, flushing toilets, watering gardens. Industrially, it's used for cooling processes, as a solvent, and manufacturing and generating power, think steam turbines again.
But agriculture is the biggest user, right?
By far. Globally, agriculture accounts for the vast majority of freshwater consumption, mainly for irrigating crops, but also for watering livestock.
And access to safe drinking water?
Mm-hmm.
It's not equal everywhere, is it?
Not at all. There's a huge global disparity. Some places face physical water scarcity, just not enough water to go around, often in arid regions.
And others?
Others might have economic water scarcity. The water resources might be there physically, but lack of investment in infrastructure pipes, treatment plants, wells means people can't access safe, clean water.
So it's about infrastructure, too.
Definitely. And there's often a big difference between cities and rural areas, too. Urban areas generally have better access because the infrastructure is more concentrated and developed.
Dams often come up as solutions for water management. What are the pros and cons of these huge projects?
Yeah.
Or where do you build them?
Multi-purpose dams can offer big benefits, no doubt. They store water for drinking, irrigation, industry. They can generate clean hydroelectric power. They can help control floods downstream.
Sounds useful. Downsides.
Significant downsides, too. Building a dam floods a large area upstream, destroying habitats and displacing entire communities. They drastically alter the river's flow and ecology downstream, blocking fish migration and trapping sediment that would normally fertilize floodplains.
So location is critical.
Absolutely. Ideally, you need a site with high rainfall in the area feeding the river, a deep, narrow valley to minimize the dam size needed for a large reservoir, solid, impermeable rock underneath to stop leaks, and preferably cooler temperatures to reduce water loss through evaporation.
Unfortunately, even the water we have can get polluted. What are the main culprits?
Pollution comes from several directions. Domestic waste is a big one. Sewage contains organic matter, pathogens like bacteria and viruses, detergents.
Industrial waste.
Industries can release a whole cocktail of pollutants, toxic chemicals, heavy metals like mercury or lead, waste heat, and sometimes gases that contribute to acid rain when they react in the atmosphere.
And back to agriculture again.
Yes, agriculture contributes significantly through runoff. Excess fertilizers, especially nitrates and phosphates, get washed into rivers and lakes, causing that eutrophication problem we talked about. Pesticides can also contaminate water.
And what are the impacts of all this pollution on people and the environment?
They're widespread. Lack of proper sanitation and sewage treatment, especially in developing countries, leads to millions suffering from waterborne diseases, things like typhoid, cholera, dysentery.
Directly from contaminated water.
Yes, industrial toxins can poison aquatic life, deplete oxygen, and accumulate in fish, potentially harming people who eat them through that process of biomagnification. Acid rain damages forests and aquatic ecosystems and even buildings. And eutrophication creates those dead zones in water bodies where little can survive.
It's a grim list. What can we actually do to improve water quality?
It needs action on multiple fronts. Improving sanitation is fundamental, providing access to proper toilets and effective sewage treatment plants to remove pollutants before wastewater is discharged.
And controlling pollution at the source.
Essential. That involves pollution control regulations for industries and farms, setting limits on what can be discharged, regular monitoring of water quality, applying the polluter pays principle so those causing pollution bear the costs of cleanup, and licensing systems for discharges.
You mentioned waterborne diseases like cholera and typhoid. Malaria is another big one linked to water, though transmitted differently.
Right. Malaria is caused by a parasite spread by infected Anopheles mosquitoes. These mosquitoes breed in stagnant water puddles, ponds, marshes.
So controlling the mosquitoes is key.
It's a major part of malaria control, yes. Vector control involves things like draining stagnant water sources, putting oil on the surface to suffocate larvae, using insecticide-treated bed nets, and spraying insecticides indoors. Antimalarial drugs are also crucial for prevention and treatment.
And for cholera and typhoid, which are bacterial.
For cholera and typhoid, the focus is really on interrupting the fecal-oral transmission route. That means improving sanitation, ensuring access to safe, clean drinking water supplies, promoting hand washing and good hygiene, treating patients effectively with rehydration therapy and antibiotics, and simple measures like boiling drinking water or disinfecting it with chlorine.
Makes sense. Okay, let's broaden our view now to the vast oceans and the resources they hold.
The oceans, yes. Huge potential. They're a massive source of food, obviously. Potential for wave and tidal energy. Huge tourism and transport industries depend on them. We can get fresh water via desalination. And they hold minerals, materials, valuable chemicals, a vast resource base.
And these huge bodies of water are constantly moving. What drives the major ocean currents?
It's mainly driven by wind blowing across the surface and differences in water density, which is affected by temperature and salinity, how salty the water is.
So wind and density differences.
Primarily. Surface currents, pushed by prevailing winds, tend to flow in big circular patterns called gyres, clockwise in the northern hemisphere, counterclockwise in the southern. You generally get cold currents flowing from the poles towards the equator and warm currents flowing the other way.
And where do we find the most fish in these vast oceans?
The richest fishing grounds are usually over the continental shelves, the relatively shallow areas around continents.
Why there?
Because sunlight can penetrate deeper, allowing phytoplankton, the microscopic plants at the bottom of the food web, to thrive. There's usually plenty of dissolved oxygen, too. This sunlit upper layer is called the euphotic zone.
Anywhere else?
Areas of upwelling are incredibly productive. That's where winds push surface water away, allowing cold, nutrient-rich water from the deep ocean to rise to the surface. These nutrients fuel massive phytoplankton blooms, supporting huge fish populations. The Peruvian anchovy fishery is a classic example of an upwelling zone.
And the opposite. Where are there fewer fish?
Generally, the deep ocean has low productivity because there's no sunlight. And warm, clear, tropical waters often have fewer nutrients near the surface, so fish populations tend to be smaller there compared to temperate or upwelling zones.
We often hear about El Niño affecting fisheries, particularly off South America. What exactly is El Niño?
El Niño Southern Oscillation, or ENSO, is a major climate pattern in the Pacific. During an El Niño event, which happens irregularly every few years, the normal trade winds weaken or even reverse.
And that changes the water.
Yes. Warm surface water that's usually piled up in the western Pacific sloshes back eastwards towards South America. This cap of warm water suppresses the normal upwelling of cold, nutrient-rich, deep water along the coasts of Peru and Ecuador.
Ah, cutting off the nutrients.
Exactly. No nutrients means less phytoplankton, which means less food for the anchovies and other fish. Fisheries there can collapse dramatically during strong El Niño events.
And it affects weather globally, too.
Oh, yes. El Niño has knock-on effects around the world. Droughts and fires in places like Indonesia and Australia, weak monsoons in India, drought in parts of Africa, but heavy rains and floods in parts of South America. It can even influence hurricane seasons.
A powerful phenomenon. Another major issue facing fisheries is overfishing. What's driving that?
It's largely down to modern fishing technology and capacity. We have huge factory trawlers that can stay at sea for months, using sophisticated sonar to find fish and deploying massive nets.
Catching too much.
Way too much in many cases. These methods are often indiscriminate, leading to huge amounts of bycatch catching and discarding unwanted species, including dolphins, turtles, seabirds. They also catch vast numbers of young fish before they had a chance to breed and replenish the stock. The result is declining fish populations despite or because of increased fishing effort.
Is fish farming aquaculture a solution to take pressure off wild stocks?
It can be part of the solution, yes. Farming fish can reduce the demand for wild-caught ones, but aquaculture has its own environmental challenges.
Such as?
Well, fish farmed in crowded pens can be prone to diseases and parasites, which can potentially spread to wild fish nearby. Also, many popular farmed fish, like salmon, are carnivores. They're often fed fish meal made from, well, wild-caught fish, often small species like anchovies. So it doesn't always remove the pressure on wild stocks, it just shifts it. Sustainability of the feed is a big issue.
Tricky. So what can we do to manage wild fisheries better?
Effective management needs a whole suite of tools. Regulations on fishing gear are important, specifying net types, minimum mesh sizes to let young fish escape. Promoting more selective methods like pole and line fishing helps reduce bycatch.
Setting limits.
Absolutely. Setting catch quotas based on scientific assessments of how much fish can be caught sustainably, the maximum sustainable yield. Implementing closed seasons during spawning times to protect breeding fish. Establishing marine protected areas or reserves where fishing is banned or restricted allows stocks to recover.
And international cooperation.
Crucial, because fish don't respect national borders. We need conservation laws within countries' exclusive economic zones, EEZs, but also international agreements, like through the UN, to manage stocks that migrate across boundaries. The big challenge, as always, is effective enforcement and monitoring of these rules.
Definitely challenging.
Yeah.
Okay, let's shift focus now to powerful natural forces that pose risks, natural hazards.
Right, natural hazards. And understanding them often starts with understanding the Earth's structure itself. We live on the crust, this thin outer layer. Below that is the thick mantle, and then the core at the center.
And the crust isn't uniform.
No. There's denser, thinner oceanic crust, mostly basalt, making up the ocean floors, and thicker, less dense continental crust, mostly granite, forming the land masses. And this crust is broken into pieces, the tectonic plates.
Which is where earthquakes and volcanoes come in. Where do they happen and why?
Their distribution is very closely tied to the boundaries where these tectonic plates meet and interact. Plate movement is driven by slow convection currents in the mantle below.
So what happens at the boundaries?
Different things. At divergent boundaries, plates pull apart. Magma rises from the mantle to fill the gap, creating new crust, like at mid-ocean ridges. This causes relatively shallow earthquakes and often shield volcanoes.
Okay, pulling apart. What about crashing together?
That's convergent boundaries. If dense oceanic crust collides with lighter continental crust, the oceanic plate gets forced underneath that subduction. This creates deep ocean trenches, generates powerful earthquakes, and fuels explosive composite volcanoes on the overriding continental plate.
Like the Andes.
Exactly. If two continental plates collide, neither wants to subduct easily, so they crumple and buckle, pushing up huge mountain ranges like the Himalayas and causing major earthquakes.
And plates sliding past each other.
That's a conservative boundary, like the San Andreas Fault. Plates grind past each other horizontally. Friction causes stress to build up, which is then released suddenly as earthquakes. Less volcanic activity here, usually.
We always hear about the Richter scale after earthquakes. What does it actually tell us?
The Richter scale measures the magnitude, basically, the amount of energy released by an earthquake at its source. It's a logarithmic scale, meaning each whole number step represents a tenfold increase in the measured amplitude of the seismic waves and about 32 times more energy released.
So a magnitude 7 is much worse than a 6.
Oh, much, much worse. Generally, below magnitude 4, you might feel it, but there's little damage. 5s and 6s can cause damage, especially to poorly built structures. 7s and 8s are major earthquakes causing widespread destruction. 9s are catastrophic, thankfully very rare.
Another type of hazard. Tropical cyclones, hurricanes, typhoons. What conditions do they need to form?
They need specific ingredients, primarily very warm ocean water at least 27 degrees Celsius or 80 Fahrenheit down to a significant depth, maybe 60 meters.
Yeah.
This warm water provides the heat and moisture that fuels the storm.
And location?
They typically form between about 5 and 20 degrees latitude, north or south of the equator. They need the Coriolis effect, the spin of the Earth, to get them rotating, and that effect is too weak right at the equator. They also tend to form during specific seasons when ocean waters are warmest, roughly June to November in the North Atlantic, November to May in the Southern Hemisphere.
Let's talk about flooding. It seems to happen in so many different ways. What are the main causes?
Flooding is complex. It can be caused by river flooding, just too much rain falling too quickly, or prolonged rain saturating the ground so it can't absorb anymore. Rapid snowmelt can also overwhelm rivers.
Land features matter too.
Definitely. Steep slopes mean faster runoff. Compacted soil, like from heavy machinery or overgrazing, reduces infiltration. Deforestation is a big factor. Trees intercept rain and their roots help water soak in. Removing them increases runoff.
And cities.
Urbanization dramatically increases flood risk. Concrete and asphalt surfaces are impermeable, so nearly all rainwater runs off immediately into drainage systems, which can get overwhelmed.
Coastal flooding too.
Yes. Storm surges, mounds of water pushed ashore by strong winds from cyclones, can cause severe coastal flooding. Tsunamis, giant waves usually triggered by underwater earthquakes, are another cause. And long-term sea level rise due to climate change is making coastal flooding more frequent and severe in many places.
The opposite problem is drought. What leads to those long dry spells?
Drought is essentially a prolonged period with significantly less rainfall than normal for a particular region. Often it's caused by persistent high-pressure weather systems that block rain-bearing low-pressure systems from moving in.
Climate patterns again.
Yes, large-scale patterns like El Niño and its counterpart La Niña can drastically alter rainfall patterns, leading to droughts in some parts of the world while causing floods elsewhere. And climate change is widely expected to make droughts more frequent and severe in many regions due to higher temperatures causing more evaporation and shifting precipitation patterns.
All these hazards, quakes, cyclones, floods, droughts, they obviously have huge impacts. Are there common themes in how they affect people and the environments?
Yes, definitely common threads, even though the specifics differ. Tectonic events, cyclones, floods, they all cause direct damage to buildings, roads, bridges, power lines. This disrupts lives, communications, economies. They can trigger secondary hazards like landslides or fires. Loss of life and injury are major concerns.
Yeah, environmental damage.
Widespread environmental damage, too. Loss of agricultural land, destruction of natural habitats like forests or coral reefs. Contamination of water supplies leading to disease outbreaks is common after floods especially. Psychological trauma for survivors is also a significant impact, and the economic costs of recovery can be astronomical.
Droughts' impacts are maybe slower, but just as severe.
Yes, drought is often called a creeping disaster. It leads to crop failures, livestock deaths, food shortages, potential famine, water sources dry up. Soil turns to dust, increasing erosion and desertification. Air quality worsens, the risk of devastating wildfires skyrockets. Ecosystems suffer immensely.
Given these huge threats, what can we do to manage the risks before, during, and after?
Hazard management is about reducing vulnerability and increasing resilience. Before an event, monitoring and early warning systems are critical, detecting earthquakes, tracking cyclones, predicting floods. Land use planning is vital, avoiding building critical infrastructure in high-risk zones like floodplains or fault lines. Building codes need to ensure structures can withstand expected forces. Disaster preparedness at community and individual levels, the evacuation plans, drills, emergency kits, is essential.
And during an event?
Effective communication of warnings, clear evacuation procedures, and providing safe shelters are key during the event itself to save lives.
Afterwards?
After the hazard strikes, the focus shifts to immediate rescue and relief efforts, medical aid, food, water, temporary shelter. Then comes the longer-term recovery, rebuilding infrastructure, providing financial assistance, psychological support, learning lessons to improve preparedness for the next time.
Are there specific strategies for floods and droughts?
Yes. Flood management often involves hard engineering, like building levees, flood walls, dams, or improving river channels. But also soft engineering, like restoring wetlands or floodplains to absorb water naturally, and better land use planning. For drought, strategies focus on water conservation, improving water use efficiency in agriculture and homes, developing new water sources like desalination or rainwater harvesting, and creating water transfer schemes if feasible.
It's interesting, you mentioned earlier that sometimes hazards can have upsides. Seems counterintuitive.
It does, but it can happen. Floodwaters, while destructive, can deposit layers of fertile silt on floodplains, which historically made areas like the Nile Valley so productive for farming.
And volcanoes.
Volcanic eruptions, despite the danger, break down over long periods to create incredibly fertile soils. They also bring valuable minerals closer to the surface, and the heat can be harnessed for geothermal energy. Tourism related to volcanic landscapes can also be an economic benefit.
So with all these risks, why do people continue to live in places prone to earthquakes, volcanoes, floods?
It's a complex mix of reasons. Often it's simply because their families have lived there for generations. There are strong cultural and community ties. Economic factors are huge. Their jobs might be there, perhaps in agriculture, on fertile volcanic slopes, or tourism.
Well, they can't afford to move.
That's a major factor for many, especially in poorer regions. Lack of resources or opportunities elsewhere prevents them from leaving. And sometimes it's perception. People might underestimate the risk, believe it won't happen to them, or have faith that protective measures will work. Or maybe the benefits, like fertile land, just outweigh the perceived risks for them.
Very complex human factors. Okay, let's move upwards now to the atmosphere, the air we breathe.
The atmosphere, yes. This blanket of gases around our planet, it has a distinct structure. We live in the troposphere, the lowest layer, where weather happens and temperature generally decreases as you go up.
Above that.
Above the troposphere is the stratosphere. Here, temperature actually increases with height. That's because the ozone layer is in the stratosphere, and it absorbs harmful ultraviolet radiation from the sun, warming things up.
And higher still.
Above the stratosphere is the mesosphere, where temperatures drop again, becoming very cold. And then the thermosphere, the outermost layer, where temperatures rise dramatically again as the thin air absorbs intense solar radiation.
And what's it actually made of?
Composition-wise, it's mostly nitrogen, about 78%. Oxygen makes up about 21%. Then there are small amounts of other gases, but they're incredibly important. Argon, carbon dioxide, water vapor, and that crucial ozone layer in the stratosphere. Each plays a role.
We hear a lot about the greenhouse effect. Can you explain the natural version?
Absolutely. The natural greenhouse effect is essential for life. The sun's energy comes in as visible light, passes through the atmosphere, and warms the Earth's surface.
Okay.
The warm surface then radiates heat back outwards, but as infrared radiation, a different wavelength. Certain gases in the atmosphere, greenhouse gases like water vapor, carbon dioxide, methane, are very good at absorbing this outgoing infrared heat.
They trap the heat.
They absorb it and then re-radiate it in all directions, including back down towards the surface. This effectively traps some heat in the lower atmosphere, keeping the planet much warmer than it would be otherwise. Without it, Earth would be a frozen ball.
So the natural effect is good, but human activities are causing problems. What kind of atmospheric pollution are we responsible for?
Yes, human activities have significantly altered the atmosphere. Smog is a big one, that hazy pollution often seen over cities. It can form when pollutants like volatile organic compounds, VOCs, and nitrogen oxides, mainly from vehicle exhaust and industry, react in sunlight. This creates photochemical smog, including ground-level ozone, which is harmful to breathe.
Temperature inversions make it worse.
They can trap the smog near the ground, yes. An inversion is when a layer of warm air sits on top of cooler air, acting like a lid.
What about acid rain?
Acid rain is caused by sulfur dioxide, SO2, and nitrogen oxides, MUOX, released from burning fossil fuels in power plants and vehicles, and also from some industrial processes and volcanoes. These gases react with water, oxygen, and other chemicals in the atmosphere to form sulfuric and nitric acids, which then fall to Earth in rain, snow, or fog.
And the ozone layer depletion.
That was primarily caused by human-made chemicals called chlorofluorocarbons, CFCs, which were widely used in refrigeration and aerosols. These chemicals rise to the stratosphere and break down ozone molecules, thinning the protective ozone layer.
Leading to the enhanced greenhouse effect.
The enhanced greenhouse effect is different. It's the extra warming caused by the buildup of greenhouse gases in the atmosphere due to human activities. Burning fossil fuels releases vast amounts of CO2. Deforestation reduces the number of trees absorbing CO2. Agriculture releases methane and nitrous oxide. These extra gases trap more heat, leading to global warming and climate change.
So these different types of pollution, what are their main impacts?
They're serious and wide-ranging. Smog causes respiratory problems like asthma and bronchitis and other health issues. Acid rain acidifies lakes and soils, harming fish and forests, and damages buildings and statues made of limestone or marble.
Ozone depletion.
Thinning the ozone layer lets more harmful UVB radiation reach the surface. This increases risks of skin cancer and cataracts in humans and can damage crops and marine ecosystems.
And climate change from the enhanced greenhouse effect.
The impacts of climate change are vast and growing. Melting glaciers and polar ice sheets contribute to sea level rise, threatening coastal communities with flooding. We're seeing more frequent and intense heat waves, droughts, heavy rainfall events, and possibly stronger storms. Ecosystems are struggling to adapt, leading to biodiversity loss. Agriculture patterns are shifting. Wildfire risk is increasing in many areas. It affects practically everything.
It's a daunting list. What can actually be done to reduce atmospheric pollution at different levels?
It really needs action on all levels. Individually, we can all try to reduce our carbon footprint. Use less energy derived from fossil fuels by conserving energy at home, driving less, using public transport or cycling, choosing energy-efficient appliances.
What about governments?
Governments have a huge role. They can implement strong transport policies promoting electric vehicles, investing in public transit, setting fuel efficiency standards. They need to support the transition to renewable energy sources. International agreements are crucial, like the Montreal Protocol, which successfully phased out most CFCs to protect the ozone layer, and the Paris Agreement on Climate Change, which sets goals for reducing greenhouse gas emissions.
Technology helps too?
Yes. Technologies like catalytic converters in cars reduce harmful emissions. Flue gas desulfurization systems, or scrubbers, can remove SO2 from power plant emissions. Governments can also use taxes on pollution or subsidies for clean energy to drive change.
And internationally, beyond agreements.
International cooperation on research and development for clean technologies is important, supporting developing countries in adopting cleaner pathways, and large-scale efforts like reforestation and afforestation planting trees can help absorb CO2 from the atmosphere. It's a global problem needing global solutions.
Definitely. Okay, let's shift focus one last time to us, the human population.
Yes, the human element. Where do people live? Population distribution and density vary hugely across the globe. Factors influencing this include the physical landscape. People tend to avoid very mountainous or arid areas. Availability of resources like water and fertile land is key. Climate plays a role.
And cultural, political factors.
Absolutely. Cultural preferences, social networks, economic opportunities, jobs, trade routes, and political stability or instability all strongly influence where people choose to live or are forced to live.
How does population size typically change over time? Is there a pattern?
Yes, populations often follow a sort of S-shaped growth curve, theoretically. There's an initial lag phase with slow growth. Then, if conditions are right, an exponential phase of rapid growth. Eventually, limiting factors, resource scarcity, disease, etc. kick in, and the growth rate slows down, leveling off in a stationary phase as the population approaches the environment's carrying capacity.
Carrying capacity.
Yeah.
The maximum number the environment can support.
Roughly, yes. The maximum population size that can be sustained indefinitely by the available resources and services of that ecosystem.
What drives the actual changes, births and deaths?
Population change is fundamentally about the balance between birth rate and death rate. Birth rates are influenced by many things. Cultural norms about family size, religious beliefs, women's education levels and employment opportunities, access to family planning, economic conditions, and the age structure of the population.
And death rates?
Death rates depend heavily on factors like access to healthcare, sanitation, nutrition levels, prevalence of infectious diseases, exposure to environmental hazards, natural disasters, and, sadly, wars and conflict.
People also move around. What pushes or pulls them to migrate?
Migration is driven by push factors, reasons to leave a place, and pull factors, reasons to go to a new place. Push factors include things like natural disasters, war, persecution, lack of jobs, poor services, poverty, or environmental degradation like desertification.
And pull factors?
Pull factors are the attractions of the destination. Maybe better job prospects, political stability, safety, access to better education or health care, availability of food or resources, joining family members already there.
The age structure of a population tells a story too. How does it typically look in richer versus poorer countries?
It does. We often use population pyramids to show the age and sex structure. In more economically developed countries, MEDCs, pyramids tend to be more column-shaped or even narrower at the base. This reflects lower birth rates, lower death rates, and longer life expectancies, resulting in a larger proportion of older people.
Oh, in less developed countries.
In less economically developed countries, LEDCs, the pyramid is typically wide at the base and tapers rapidly towards the top. This shows high birth rates, a large portion of young people, and higher death rates at younger ages, meaning fewer people reach old age.
Managing population size is a sensitive issue. What strategies are used?
Strategies vary hugely. Many focus on factors that tend to naturally lower birth rates, like improving education and healthcare, especially for women and girls, and increasing economic development. Providing access to voluntary family planning services, information, and contraception is a common strategy.
Are there direct government policies?
Yes, some governments have explicit population policies. Some, facing aging populations and low birth rates, might have pronatalist policies, offering incentives for people to have more children. Others, concerned about rapid growth outstripping resources, have implemented antinatalist policies to encourage smaller families, like China's former one-child policy, though these can be controversial and have unintended consequences.
Complex indeed. Okay, for our final segment, let's dive into natural ecosystems and how human activities affect them.
Right, ecosystems. An ecosystem is basically a community of living organisms, plants, animals, microbes interacting with each other and with their physical environment, the non-living or abiotic factors.
Can you break down those terms? Population, community?
Sure, a population is all the individuals of one particular species living in a specific area. A community is all the different populations of different species living and interacting together in that area. The habitat is the physical place where an organism lives, and its niche is its role or job in the ecosystem, what it eats, where it lives, how it interacts.
And the living versus non-living parts.
The living parts are the biotic components. Producers, like plants that make their own food through photosynthesis, consumers, like animals that eat plants or other animals, and decomposers, like bacteria and fungi that break down dead organic matter. The non-living abiotic components include things like temperature, sunlight, water availability, soil type, pH, salinity, oxygen levels.
How do the living things interact?
In countless ways. Competition happens when organisms need the same limited resources. Predation is when one organism hunts and eats another. Pollination is often a mutualistic relationship where both the plant and the pollinator benefit. These interactions structure the community.
Energy flows through these systems.
Yes, energy flow is fundamental. It usually starts with producers capturing solar energy via photosynthesis, using chlorophyll to convert light energy into chemical energy stored in sugars.
And then it moves up the food chain.
Exactly. Energy flows from producers to primary consumers, herbivores, then to secondary consumers, carnivores or omnivores, and so on, forming food chains. These chains interconnect into complex food webs. Each step is a trophic level.
And ecological pyramids show this.
Yes, pyramids of numbers, or more accurately, pyramids of energy or biomass, illustrate how the number of organisms, the total mass or the total energy, decreases significantly at each higher trophic level. A lot of energy is lost at each transfer, mainly through respiration, the process organisms use to release energy from their food.
And materials cycle too, like carbon.
Absolutely. Nutrients like carbon, nitrogen, phosphorus are constantly cycled between the living and non-living parts of the ecosystem. The carbon cycle, for example, involves CO2 being taken up by plants, moving through food webs, being released through respiration and decomposition, and exchanging with the atmosphere and oceans. It's crucial for climate regulation.
But human activities are putting huge pressure on these ecosystems, often through habitat loss.
Habitat loss is arguably the single biggest threat to biodiversity worldwide. And yes, humans are the main driver. Draining wetlands is a major cause. Wetlands are incredibly productive ecosystems, but they're often drained for agriculture, forestry, or development.
What benefits do wetlands provide?
Oh, huge benefits. They act as natural filters, improving water quality. They absorb floodwaters, protecting downstream areas. They help recharge groundwater supplies. They stabilize shorelines. And they support an immense diversity of wildlife. Losing them is a major blow.
Intensive agriculture, too.
Yes, converting natural habitats like grasslands or forests into vast fields of single crops monocultures drastically reduces biodiversity and can degrade the soil. Deforestation, clearing forests for timber, farming, ranching, or infrastructure is another massive driver of habitat loss.
And the consequences of losing these habitats.
The consequences are severe. The most direct is loss of biodiversity, fewer species, smaller populations. This leads to genetic depletion within the remaining populations, making them less resilient to change or disease. Ultimately, habitat loss is the #1 cause of species extinction. It weakens the whole ecosystem, making it less stable and less able to provide the services we rely on.
Deforestation seems particularly damaging. Can you recap the causes and impacts?
Sure, forests are cleared for timber, for paper pulp, for fuel wood. Huge areas are cleared for farming crops like soy and palm oil or cattle ranching. Mining operations and infrastructure like roads also drive deforestation.
And the impacts?
Habitat loss for countless forest species is the immediate impact. Loss of biodiversity. Increased soil erosion because tree roots no longer hold the soil and the canopy doesn't intercept rain. This can lead to landslides and desertification. And, crucially, deforestation contributes significantly to climate change. Trees store vast amounts of carbon. Burning or clearing forests releases that carbon as CO2 into the atmosphere.
Given how vital forests are, how can we manage them sustainably?
Sustainable forest management is crucial. It means using forest resources in a way that meets our needs but maintains the forest's health, productivity, and biodiversity for the long term. Forests provide habitat, genetic resources, vital ecosystem services regulating water cycles, storing carbon, preventing erosion. They provide timber, food, medicine, ecotourism potential too.
What's the difference between a carbon sink and a store?
A growing forest actively removing CO2 from the atmosphere is a carbon sink. A mature forest holding large amounts of carbon in its trees and soil is a carbon store. We need both. Sustainable practices include things like selective logging instead of clear cutting, reduced impact logging techniques, reforestation, replanting cleared areas, afforestation, planting new forests, and agroforestry, integrating trees with crops or livestock.
How do scientists actually measure biodiversity in an area?
They use various sampling techniques because counting everything is impossible. For ground-dwelling insects and spiders, they might use pitfall traps, basically containers sunk into the ground that creatures fall into. Pooters are little devices used to gently suck up small insects from leaves or flowers.
And for plants or less mobile things?
Quadrats are commonly used. These are square frames of a standard size. Scientists place them randomly or systematically within the study area and count the number of species or individuals inside each quadrant. Transects involve laying a line across an area and sampling at regular intervals along it, often using quadrats, to see how species change along an environmental gradient. These methods allow estimates of species richness and abundance.
And these techniques can be adapted.
Oh yes, the principles can be applied in many different situations to get a snapshot of the biodiversity.
Finally, what strategies are being used, nationally and internationally, to conserve biodiversity and genetic resources?
There's a wide range. Sustainable harvesting aims to use wild populations, like fish or timber, at rates they can sustain. Sustainable forestry and agroforestry, as we mentioned. Stronger environmental laws and enforcement are key.
Protected areas.
Yes, establishing national parks, wildlife reserves, marine protected areas, and corridors connecting them is a cornerstone of conservation, protecting critical habitats. Extractive reserves try to combine conservation with sustainable resource use by local communities. UNESCO's World Biosphere Reserves aim for zoned areas balancing conservation, research, and sustainable development.
What about off-site conservation?
Seed banks are vital for preserving the genetic diversity of plants, storing seeds from thousands of varieties. Zoos and botanical gardens play a role through captive breeding programs for endangered species, aiming for eventual reintroduction to the wild if possible. And sustainable tourism, or ecotourism, when done right, can provide economic incentives for local communities to protect wildlife and habitats. So as we've really explored across this whole deep dive, the Earth's systems, rocks, water, air, life, they're all profoundly interconnected.
Absolutely. Intricate systems.
And our human activities, well, they ripple through these systems in ways that are often far-reaching, sometimes ways we're still figuring out.
It feels abundantly clear, doesn't it, that understanding these complex relationships isn't just, an academic thing. It's absolutely essential.
Crucial.
For making informed decisions, whether it's in our own lives or shaping policy on a bigger scale. It's all about fostering sustainability, ensuring a healthy planet for the future.
Yeah, this whole deep dive really highlights that fundamental tension, that balance we have to strike between using the resources Earth provides and conserving those systems for the long haul.
A delicate balance.
And navigating that balance, well, that responsibility really falls on all of us, doesn't it? It makes you think, what role do you play in these global challenges? Is there more you want to learn? Are there actions, small or large, that this information might inspire you to take?
That's a really powerful thought to end on. We sincerely hope this deep dive has given you a valuable shortcut, a clearer lens for understanding these critical, interconnected issues.
We'll keep digging into other fascinating topics in future deep dives.
And we always welcome your input. If you have source materials or topics you'd like us to explore, do let us know. Until our next exploration, keep questioning, keep learning.
And keep exploring the amazing world around you.